So my name is Craig Bingman, and this is my talk on Limewater for MACNA. Before I get into it, I hope that you've had a chance to watch Reef Beef episode 55 and also to complete the calcification survey that you'll find on my webpage for MACNA 2022. So without any further ado, let's ask some questions about Limewater, or questions you might have. Who am I and why should you listen to me? What is Limewater? Who thought up Limewater? Why would you care about it? How do you use it? How can you misuse it, which is a very important subject with Limewater? And is it better than other things that you might use? So Limewater's really literally part of my creation story in the aquarium world. It was, I believe, the second subject that I wrote about on Usenet in the very early 1990s. Subject that I've thought about very deeply and for a long time. I find it really interesting, actually, that people are interested in Limewater again. It, for me, is a little bit like, opening up my closet and finding out that clothes that I bought 3 decades ago are suddenly back in style. So that's fun. I was approached this spring to give a couple of Zoom talks to clubs that were having their meetings, online. And the subject of Limewater kept coming up. And so I decided it might be fun to give a talk for MACNA on that subject. I also thought it might be interesting to pre-record my lecture so you could listen to it a little bit in advance and then spend most of the lecture on questions that you might have, or diving more deeply into some parts of the subject that I might have glossed over during the talk. So these are the origin Usenet posts for me. I think the first one was about potassium permanganate, and then I really got sucked into discussion about Limewater and calcium carbonate, or calcium chloride and sodium bicarbonate. People had a really rough time of it when people began keeping corals in captivity. When I got involved, there was an appreciation that you had to supplement both calcium and carbonate alkalinity to keep them alive. Corals use this stuff up very rapidly. And people suddenly had this sort of tiger by the tail and didn't really quite know what they were getting into or exactly how to go about, keeping it steered in a good direction. So that's what I started thinking about when I started thinking about marine aquariums. Limewater itself is the original balanced calcium alkalinity supplement that does not have, that is a one-part supplement that has calcium and alkalinity present in the ratio that you need to form coral skeleton. That's a very important property, and it was what really messed people up early on with calcium chloride and sodium bicarbonate, because people would buy them, wherever they got it, snow melt, baking soda, and make up their own solutions, which were arbitrarily formulated, and then dose the stuff in some volumes. And they were constantly testing for calcium and alkalinity tests, and it was all over the map. They just could not keep things balanced. Limewater itself comes with this balance built into the substance. It's made by driving carbon dioxide off from lime, and it's made by driving carbon dioxide off of calcium carbonate, and therefore in its native stoichiometry, the native ratios of things, it has that balance intrinsically built into it. So that's pretty cool. Lime water, as discussed in the hobby, is made by dissolving calcium hydroxide in water, usually as formed in a saturated solution, sometimes supersaturated. We'll talk about that a little bit later on. At 25 degrees C, it contains about 20 millimolar calcium ions. Seawater is 10 millimolar, so the calcium concentration in lime water is about double that you find in natural seawater. The amount of alkalinity is much higher than you find in seawater, which would be about 40 milliequivalents per liter. Is a concentration of alkalinity in lime water. So, what is it? People use the word lime to mean a few different things. Lime in the aquarium hobby is usually means slaked lime, or lime that a little bit of water's been added to hydrate it. So it's hydrated slaked lime, calcium hydroxide. The unhydrated lime, the thirsty lime, is calcium oxide, which people sometimes call burnt lime. The hydration of calcium oxide is really exothermic, so it liberates a lot of heat. It's a moderately dangerous substance to have around, especially if you have young children, pets, that might get some of this in their mouth or in their eyes. In addition to being highly alkaline, it does generate really a whopping amount of heat when it's hydrated, and it can cause thermal burns in addition to burning someone chemically. Very occasionally, people use calcium carbonate, lime to mean calcium carbonate, as in a farmer will lime their field with very finely ground calcium carbonate. That's not common in the aquarium hobby, and I won't use the word in that sense. Calcium hydroxide and solutions of calcium hydroxide have almost no magnesium in them. This becomes important later on. Magnesium is really almost completely insoluble in saturated solution because the hydroxide ions, aside from trace impurities, lime water consists just of calcium ions and hydroxide ions in water. Some people used to use it to reject phosphate in their top-off water. That use, it does that. It will take phosphate concentrations down to about 0.02 megs per liter as saturated and settled lime water. That's not true. If it's not saturated or it's not settled, then the sludge in the bottom of your lime water basin can contain not just calcium hydroxide, but also the other impurities are accumulated there. It contains almost really no carbonate or bicarbonate ions whatsoever. That's what corals need. So we have like a little bit of a conundrum here. How is this going to work? It's got like balanced calcium and alkalinity, but the alkalinity is not in the form that's immediately useful to us. So this alkalinity stuff, you may have heard that corals need bicarbonate or carbonate ions. That's true. Lime water has hydroxide ions. How do you get from point A to point B? And the answer is that the hydroxide ions in lime water will neutralize carbon dioxide. If the solution will absorb carbon dioxide from the atmosphere extremely rapidly, you'll see a skin forming on top of it within minutes of exposure to air. And that thin skin, which will start to form and get heavy and then fall down to the bottom of the basin, is calcium carbonate that's forming at the air-water interface, because that's where the carbon dioxide is getting into the solution. So how does this work again? So we put the lime water in our aquariums, and then the higher pH causes more carbon dioxide to dissolve and get hydrated and make bicarbonate ions, according to the formulas on the left side of the screen. The first reaction, which is hydration of CO2, is very, very slow. And all life on Earth, I think, has an enzyme called carbonic anhydrase, whose sole job it is to catalyze this reaction and make it go faster. It's an incredibly important reaction to go fast, say in your lungs where you're trying to do gas exchange, or other places in biology where you need to convert CO2 into a form that you can actually do something with. And corals have a lot of carbonic anhydrase as well. The second reaction, which is deprotonation of carbonic acid to form bicarbonate, is diffusion limited in water. It's extremely fast. So you have like this turtle of a reaction and one blazing fast reaction that happens after that. So maybe you should just add carbon dioxide to lime water, right? That'll solve our problem. No, it won't. All you'll do is you'll just make this sludge in the bucket. So what you need to do is kind of sneak up on the situation, dose calcium hydroxide lime water into your aquarium very gradually, allow this reaction with carbon dioxide to occur at the full dilution of the substance in your aquarium, and then it can be effective. It can really do a great job of, say, raising the pH in your aquarium, and neutralizing carbon dioxide. So you have to dose lime water gradually. Many people will dose it overnight. You really need a dosing pump to use it effectively. You need a reliable dosing pump, one that you don't have to worry about it not doing exactly what you tell it to. There are some other concerns as well, which we'll discuss in just a bit. So the amount of carbon dioxide that you have available may or may not be sufficient to neutralize the hydroxide ions in lime water. So this "may" word may not fill you with confidence, and it's really not meant to make you super confident. It's made to make you evaluate what you're doing, and make sure that you're not overdoing it with lime water. So you do need this mechanism to dose it slowly. You do need to make sure that you don't dump it into the aquarium. And you need to make sure that you don't take the sludge off of the bottom of the lime water dosing bucket in the course of your dosing operation, unless your intention is to dose milky lime water to get more of it in. Now, the milky lime water is really, if lime water is a tiger, that's like a really extremely angry tiger, and you have to be very careful with that. So what happens if you just dump lime water into your aquarium? Well, that's why I wanted you to watch episode 55 of Reef Beef. There's a really great discussion of an event like that happened with someone who watches Reef Beef. And I'll just let you look at it, think about it. I'd like to discuss that episode a little bit in the lecture. There's a QR code here, so I think if you take your phone to the screen and turn your camera on, you'll have the option of bouncing directly to that YouTube episode right now. We'll just keep going, so you can hit pause on this and come back to it later. So another example of an adverse situation that was caused by lime water was presented a few months after I gave my talk to the North Carolina group, or the Carolina group. Oral was experimenting with a bunch of different ways of maintaining his aquarium, and he turned to lime water because it was, people were talking about it again. It was the cool thing to do, I guess. And in the course of learning how to do that, he inadvertently got in a situation where I believe he dispensed the lime slurry from the bottom of his Limewater basin. And as you're using lime water, you kind of like dump in some calcium hydroxide, which is usually in excess, and then you mix it up and you let it settle out. And you don't necessarily dump out the basin every time, or maybe you're trying to play with supersaturated or turbid lime water. So there's always excess calcium hydroxide in the bottom of the bucket, basically. And if you put that in your aquarium unknowingly, what happens is what you see in the slides, right? So the aquarium became completely opaque. People call this a snowstorm. You might want to call it something else. You can see some expensive dead fish on the bottom of the aquarium. And this was a really bad wipeout. So I think that there was almost complete loss of complex life in the aquarium. I think a pair of clownfish somehow miraculously survived this, but everything else was gone. All the other fish, the corals, everything else. So you want to avoid this is a possibility with lime water that you need to be aware of. I never did this personally. I did manage to dose enough lime water to cause my pumps to need to be cleaned out with acid in the course of learning exactly how to do this and chasing ever increasing calcification rates in my aquarium, which was really just completely confluent with SPS corals. So that was a wild ride. But I didn't, this is not an inevitable consequence of dosing lime water. You don't have to have a wipeout if you're careful. It's not a rite of passage. It's something that you can think about and avoid. So don't necessarily, bail out on me at this point in the talk. I'm sort of front-end loading the adverse parts of lime water so that you're aware of them and they're well represented. But lime water really does have some unique benefits, I think, that make it worthy of everyone's attention who's doing coral husbandry. So I think that the chief benefit, and this is sort of a subtle one actually, is that it sort of almost magically pushes your aquarium in the direction that favors calcifying organisms and disfavors like nuisance algae. So how might lime water accomplish this phase change in your aquarium? To back up a little bit, it's known that reefs can find a stable equilibrium in at least two different phases, where one of which is really dominated by algae and the corals lose. A lot of that's happening in reefs around the world that are subjected to various pressures, some of which may be overfishing. People like to blame nutrients in a lot of cases. That definitely that has some impact, but wherever you've got a nutrient problem, I think there's also a human problem, and the humans are fishing, and skewing the balance of organisms on the reef away from, say, parrotfish who eat a lot of algae, and you eat all the parrotfish, and then suddenly you've got a problem on your hands. Another way that you can push, so the other stable phase is really like dominated by calcifying organisms, coralline algae. There's really no big open surfaces exposed for nuisance algae to get a foothold. Corals and coralline algae are able to boost their photosynthesis by tapping into bicarbonate ions in seawater. And they do that by forming calcium carbonate. And when you make calcium carbonate from water with bicarbonate ions in it, you basically generate a free carbon dioxide. And that can go straight into photosynthesis. So you're calcifying and boosting your own photosynthesis. This is not like a one-to-one ratio in corals. I think that the ratio is usually something like if you have one unit of photosynthesis by carbon atoms, you'll have 0.6 units of calcification. So there's a little bit more photosynthesis than calcification, but calcification is competent to supply really the majority of carbon dioxide required for photosynthesis and in reforming corals. So other organisms that have to kind of like pry carbon dioxide out of the water don't have that advantage, and they can get kind of like shoved out of the way. The corals will outgrow them. Coralline algae will outgrow them. And the way that you do that is by controlling carbon dioxide in your aquarium. Okay, so it's known that ocean acidification ocean acidification may have impacts on reefs and other scenarios in the ocean, and people have been studying that pretty hard for a while, since we've realized that atmospheric carbon dioxide is increasing rapidly. So in one study that you can read by, again, using the QR code, that'll take you to a URL where you can at least read the abstract, if not download the whole paper. I've tried to pick up URLs that have free versions of the article, so you won't be behind a paywall. But in this study, they showed that high carbon dioxide in the ocean makes coralline algae less tolerant of different light fields and less tolerant of high light. And this may be important in aquariums too. So if you have low carbon dioxide in your tank, your coralline algae may, because light and photosynthesis are intertwined, and if your photosynthesis is not running as well as it should because it's short of some material that's required for it, things can get kind of pile up and make toxic intermediates. So the coralline algae are better at photosynthesis and feeding themselves at lower carbon dioxide concentrations, which is pretty interesting actually. And maybe part of the reason why using lime water can affect these phase changes. So let's dive now into a little bit more about the properties of lime water. So one of the things that I'd like you to know about lime water is that it becomes less soluble at higher temperatures. So some people will have their lime water basin underneath their tank in their sump area, which is notoriously warm and notoriously high in carbon dioxide, right? So that's where you've got a bunch of gas exchange happening, outgassing of carbon dioxide from the aquarium, and it can really build up in there, and it's warm. So that's going to make your lime water not last as long and become less concentrated. So you can see, in the table, which you can pause at any point and look at it in detail, that in fact lime water does become substantially less soluble as the temperature increases over a range that you might easily find, at room temperature or in a warm sump area. So keep that in mind. As part of the articles that I wrote, I was looking to help people understand how much lime water would be required to support different calcification scenarios in different aquariums. So the numbers, there's this rainbow color gradient here, and the numbers run from 1 to 15. And those numbers correspond to what I would call a calcification unit. So the units are kilograms of calcium carbonate per square meter per year. And we'll just call that a calcification unit. And we know how many calcification units you would expect different aquariums to require, to support how much calcification will occur in the aquarium with different benthic communities. So you have a bunch of sand and a little bit of coral, you're not going to need as much calcification support. You have kind of like wall-to-wall SPS, then that's the worst case scenario. That those systems will require a lot of support. So they'll perform many calcification units of calcification per year. So if you know what that number is, and we can talk about that during the lecture, and I hope to have a companion video to this, which is quantitative calcium alkalinity, and it's also a product of the calcification survey. So that's we want to understand more about what those numbers are in real reef systems, so that we can make more accurate predictions for what people need. But obtaining that number, and let's say that for kind of an average mixed reef, the number that you're looking at may be 4. For a confluent SPS tank, the numbers that you're looking at may run from 10 to possibly even as high as 20 on this graph. So you can see that there's a big difference in the amount of lime water that you need to support 4 and to support 10 or 15, right? So I've also on this graph kind of like drawn lines for some common US dimensioned aquariums. So 55, 75, 180 gallon aquarium and the most common glass aquarium dimensions on here. And if you've got a system like that, you can, or if you have a different system, you can figure out what its bottom area is in square meters and locate it on these graphs. And then you start from, say you have a 180 gallon tank and it's a mixed reef, and you have an expectation of 4 calcification units. You'll need to evaporate about 6 liters per day and replace that with saturated lime water stored at 25 degrees C to break even on calcium and alkalinity. So that's not an incredibly high evaporation rate for a 180 gallon tank. But let's say that your calcification rate is much higher, and you've bumped it up above 10 and like 15 calcification unit territory. So in that case, you're looking at 22 liters. It's about 4 liters per gallon. So you're looking at, over a 5 gallon bucket of top off water a day that you have to bring in to keep that aquarium from dropping alkalinity and calcium. And that's much harder. That's going to have an impact on the comfort of your home. Evaporating that much water will make the whole place more humid. It'll make the place your home feel clammy, probably. And people may just not want to do that, right? So you may want to intentionally limit the evaporation from your aquarium to a smaller value to increase your comfort in your home. And that just means that the lime water equation is not going to work out for you by itself. So it may be a good supplement for you, but you're not going to be able to get there with the amount of evaporation that you can tolerate from your system. And that's just the way it is. We knew that in the 90s. That's how it is, guys. Look at these graphs. You can, if you do the calcification survey, I'll give you back, the expected numbers for your aquarium, and you can locate yourself on the graph and figure out exactly what the story is. So this is old news, but I don't know how many people remember this story, because this story was told in the last millennium. So here's the graph. You can do your homework and figure out where your tank is, or if you do the calcification survey, I'll do the homework for you. Because this was a problem, let's see. I guess I didn't put the QR code on that one, but I do have a QR code here for an article that I wrote about expanding the limits of lime water. Oh, that's right. That's because the last one was in print. So to make lime water work a little bit better, I suggested that people could add 5% acetic acid, which is the strength, the concentration of vinegar, most commonly in the United States. So if you add 12 mils of vinegar per liter of water, that's about 4 tablespoons per gallon, that'll raise the calcium concentration and ultimately the alkalinity, effective alkalinity in lime water by about 40%. So you can get a lot, you can support higher calcification scenarios with the same volume of evaporation. And this is a nice number because that amount of vinegar is about the amount of when it's oxidized, and corals actually use acetate directly. So the corals will help out with this process of turning acetate ions to carbon dioxide and bicarbonate ions. But that provides you with just the right amount of just about the right amount of carbon dioxide to neutralize the hydroxide ions in the lime water. Most people don't have problems with this system. It's a cheat that you can get away with up to about this level. Beyond this point, you may have problems with clumping in your sand. That's probably caused by bicarbonate ions being formed by bacteria in the sand and causing the sand to kind of turn into concrete, which you can work around. Some people say that cyanobacteria may show up at higher acetate concentrations as well. So it might be helpful to you to do this. And the QR code will take you to one of those articles that I wrote. You may have heard that lime water precipitates magnesium. And so that's like kind of true. If you dump a bag of lime in a volume of seawater, it will precipitate magnesium hydroxide. And that's a way of actually making magnesium hydroxide from seawater, isolating magnesium in pure form from seawater. But in the scenario where you're using lime water, there's really, that kind of doesn't happen. It's only in these gross overdose scenarios that you'll get the formation of magnesium hydroxide, and there's probably some magnesium hydroxide in the, let's see, which way does it go? I've got the camera reversed so that you can read the reef beef sign behind me. But there's probably some magnesium hydroxide there. I don't think it's a big issue with dosing clear lime water in aquariums. What people are really seeing, I think, is that there's a substantial biological demand for magnesium in our reef systems, and lime water just doesn't have any of it. So when you add magnesium-free calcium support, your magnesium will drop because someone's using it. So who's using it? Well, it's probably coralline algae mainly. Talk a little bit more about that later on. So back to the limit breaking. Before I proposed using acetate, Alf Nielsen popularized dosing lime water suspensions and using active pH control. So there's a pH probe controller that controls the dosing of carbon dioxide in the system. There's a reactor that maintains supersaturated milky lime water that you can inject on demand into your aquarium. This makes lime water more effective. It certainly allows you to support more calcification with a given amount of evaporation from your system than you would otherwise. And if you go to this QR code, you can listen to Alf's discussion of Alf's MACNA award that he recently received from MACNA. And there's a reactor discussion at about time mark 29:45. So you can listen to that and other fascinating things about Alf's life. coralline algae and magnesium in lime water. So if you hit the QR code under the coralline algae make dolomite header, you can read the first article that really reported that coralline algae are able to make equimolar calcium magnesium carbonate, which is dolomite. And it's been observed to exist on reefs for decades. And finally, someone really put it together that it wasn't some abiotic process that was creating it that we didn't understand. Dolomite's usually found or formed kind of like deep in the earth as a long process that happens over thousands or millions of years. And it's really weird to find it in these extremely young carbonates that were made, like yesterday on reefs. So people have now pinned down coralline algae as the culprits. More recently, people, if you look at the second QR code, some people have even found that coralline algae will precipitate in some controlled compartments magnesium hydroxide from seawater. So they're going, all out and stealing a bunch of magnesium from the aquarium. Now, is that a bad thing? No, I think it's a great thing, because I think coralline algae are fantastic, and I think that they're fantastic largely because, well, they're kind of pretty. They're colorful, and they also take up turf that surface area that nuisance algae can't colonize. So I've never seen nuisance algae growing directly on coralline. It's always kind of like, sprouting out at the edges between whorls of coralline algae, or somewhere where someone took a bite or something else on the rocks. It just does not seem to be able to gain a foothold on surfaces that are completely encrusted with coralline algae. So I view it as large, incredibly valuable, and we just need to figure out how to support it, right? So it's like, if you want coralline algae, and I think you should want coralline algae, you're going to have to figure out how to dose magnesium to your aquarium. That's a subject for another day, I suppose, another talk. So it's like people wanted to control nutrients by starving their fish, basically, and that's another like catastrophically bad idea, right? So don't go on a war to eradicate coralline algae because they use up magnesium. We're smarter than that, and don't starve your fish, because that's just really bad too. So to kind of like pull things together, Limewater has the lowest carbon dioxide partial pressure of any calcium alkalinity supplement that we have. That makes it the most effective in mopping up excess carbon dioxide and pushing our systems towards supporting calcifying organisms, giving them an advantage. The chemical is relatively inexpensive if you get USP, calcium hydroxide. The need to have some reliable dosing equipment does increase the cost somewhat, but it's still pretty inexpensive. It's exceptionally magnesium poor. No poorer than magnesium, in magnesium than the purified calcium chloride that you might get. But definitely no magnesium's coming in with lime water. And you need to take great care not to dose it too quickly. And we can talk more about that at MACNA. So some topics that I think might be interesting for us to talk about are, like what fraction of the audience uses lime water, how many people have had adverse events, what practical things people are doing to dose it safely. Do people think I'm full of it when I say that it helps push your aquarium towards a calcifying phase and away from a algae-dominated phase? And when people are measuring lime, how do you do that? It's by mass, by volume, let's get in and talk about the nitty gritty of using lime water in current practice. So thanks for your attention. This is my first pre-recorded video, my first flip lecture, and I look forward to seeing you all at MACNA.